So let's talk about electrical connections between the FPGA and a DB15 connector that you would connect your VGA cable to. So on this side, we have the FPGA, and these are just FPGA output pins. Note that those output pins output 3.3 volts. So any 5 pins from your FPGA that can output a digital signal will work here. I'm not even going to name a specific pin. Any board will work that has 5 digital outputs. So I'll just arbitrarily list them here. But we'll go ahead and label them here by what their assigned function will be. This will be the red, the green, the blue, and then the horizontal sync and the vertical sync. Now over on this side, we've got the DB15 VGA connector. So the DB15's got 15 connections on it, obviously. I need more spots. Okay. So this is pin 1, 2. So first thing is the monitor, which, you've got a cable that connects over to the monitor. The specification would say that the RG and B signals in the physical monitor itself have I'm going to write this down. The RG and B signals have a 75 ohm impedance. So what this means is that to this circuit, which is driving the signals over to the monitor, what these signals actually see are, so I'm just going to put RGB. What they actually see is a circuit that looks something like that. They will see a 75 ohm characteristic impedance. Now, the specification also says that the input voltages to RG and B should be somewhere between, so the input voltage should be somewhere between 0 to 0.7 volts, right? So now maybe you can see an interesting quandary here, right? So if your output, if RG and B are outputting 3.3 volts from the FPGA, and you put 3.3 volts in here as the highest voltage, well, you're exceeding the spec and you might damage the monitor. Probably not, because most monitors are built robustly, but certainly you're exceeding the spec. There needs to be a way to get these voltages down to 0.7. Well, how do you do that? Very simple voltage divider. That's done with a series resistor. So if you think about it, if you have a driving voltage over here, all right, and a resistor here, and a resistor here to ground, well, at this point, you can get voltage drop through this resistor divider network. And we know what this resistance value is, right? It's 75 ohms. We don't know what that one is. That's what we're trying to figure out. So we want the voltage drop across this resistor to be 2.6 volts. And we know the voltage drop across this resistor needs to be a maximum of 0.7 volts. So we can figure out what the current flow through this resistor will wind up being by using Ohm's law. And so in this case, 0.7 volts got to be equal to the current times 75 ohms. And so in that case, the current's got to be equal to 0.009 amps. Okay, so that then means that to to calculate the value of this resistor, our voltage in this case must be 2.6 volts equal to 0.009 amps times X. So in this case, then X has got to be, let's see, 2.6 divided by 0.009. It's got to be equal to 288, now more or less, ohms. So, common value is 270, I think, ohms. However, I didn't have one or couldn't find one easily. And so I wound up using 220 ohm resistor. So what that means then is that to pin 1, which is the red pin, there needs to be I'm going to call it 270. Again, I use 220, but if you want to be more technically correct, 270 is what you need. So leaves the horizontal and vertical sync. The horizontal sync is pin 13. So this is horizontal sync, and vertical sync is pin 14. I think in theory you could just wire them up together and it would probably work. However, the cable that connects the FPGA to the monitor will have some capacitance in it. And in order to sort of dampen instantaneous current draws on something with capacitance, you can use an RC network to kind of filter that out. I sort of assumed that the characteristic impedance of the FPGA is about 25 ohms. I think the impedance of the line is 75 ohms or thereabouts. So that means you need to add roughly a 50 ohm resistor in series. So again, it can act as impedance matching as well as dampening based on capacitance in the line. And the final reason that you'd want to do this would be shorts. So if the monitor presented a short to your FPGA, you wouldn't want your FPGA to blow up. So put a little current limiting resistor in there that would limit current. So what I wound up doing is a resistor of 47 ohms, assuming 50 plus 25 is 75, giving you, the impedance matching. I've seen people do 100 ohms, maybe even up to 400 ohms. You don't want to attenuate your signal. There won't be much drop at all from the monitor, but you don't want to attenuate your signal very much below. I believe these signals have to be somewhere between 3.3 volts and 5 volts. So you don't want them to drop, much below 3.3 volts, and that's what's coming out of the FPGA. So ground, there's actually 4 grounds you have to connect. The grounds are, let me look at my schematic. So pin 6, pin 7, and pin 8. So all of those have to be wired together to ground, just like that. Let's put together a simple test harness that'll test out the current state of our 2 pulse generators, and let's just simply output all ones, which will be all white pixels. Probably take a few measurements also of the waveforms because it sort of enters into the electrical discussion. So obviously we need a sync pulse generator, and we need our our porch and margin generator, and we'll need a clock. And we'll need some constants. So our horizontal count and our vertical count just get wired across these 2 components. And these two components share the horizontal and vertical pixel count. So I'm going to go ahead and I guess wire some tunnels. And then we need constants for these values over here as well. Oh yeah, made a mistake. These are not counts. These are the polarity signals. So we'll actually put polarity on here in a second. Let's go ahead and wire our outputs up. Each one of the RGB bits, we're just going to output a 1 or 0. In this case, when we are in the active area, then the bit goes high for active, and so that means it's going to turn the actual bit on for the displayable area. So in order to fill in our constants, I'm going to go to this trusty video timings calculator page. The link's in the description. And I selected 640 by 480 at 60 Hz refresh, which is a predefined mode. And so in this CVT column, I'm going to translate the counts required to fill in the constants on the design. These have to, of course, be translated into hex. And I'm going to go ahead and flip over and fill these in. Oh, and also notice the polarity. The H-sync polarity is negative, and the V-sync polarity is positive. So let's go ahead and fill those in. So horizontal sync negative. And remember, positive going is a 1, so this needs to be a 0 or ground. And this needs to be the opposite. Okay, so now I'll fill in all the constants. Now, in terms of the margin, that's not on the calculator. And so, given that it's a 640 by 480 resolution, but our hack display is a 512 by 256, basically you subtract the horizontals and divide by 2, and you subtract the verticals, divide by 2, convert to hex, and then you wind up with both the horizontal margin and the vertical margin. Okay, let's synthesize this. Now again, our clock frequency, if we flip back over here, is saying the pixel clock needs to be 23.75. I'm not going to get that precise. I'm just going to go to 24, just kind of round it up. And so, which I think should be close enough. It may boost the refresh frequency a slight amount, but the monitor doesn't really care. So to get that, with our Digilent board, we need a tick frequency of 48 megahertz in order to get half of that, a clock frequency of 24 megahertz. Now I have RGB pins mapped to my VGA connector that are in these 3 spots down here. R, G, and B, I forget which is which, doesn't really matter because they're all going to be the same anyway. So I'm just going to map them sort of haphazardly. However, horizontal and vertical sync absolutely do matter. And the way I have this wired right now, this pin here is the horizontal sync, and this pin is the vertical sync. Okay, synthesis finished. Looks like it was successful. load the design. So let me flip over to my board and scope. So the first thing, I'm not going to hook up the VGA just yet, but what I will do is I want to look electrically to make sure that the signal outputs that we are getting, are sort of within a reasonable range of what we expect based on our electrical connections. So I'm going to just hook up to one of the RGB pins, doesn't matter which one, my scope, and let's see what the signal level is on one of the display pins. So I'm going to program. And well, of course, it's showing 3.3 volts, which is what is expected because I actually don't have the VGA connected. Because remember from the electrical discussion, there's a voltage divider that is formed between the monitor and the board itself. So I would expect the voltage to be, with it disconnected, I would expect it to be showing full voltage. But what we are seeing is definitely pulses being output. So let's instead, I guess we'll plug the monitor in and look at some voltages. Well, on closer inspection, what we can see is that our pulses are definitely below. This is 1 volt. It's a 1 volt scale, and they are definitely below 1 volt. So my resistors may actually be fairly close. What is interesting is you see overshoot, slight bit of overshoot and an undershoot, which is what my scope is measuring. I don't know whether the overshoot and the undershoot matter from the monitor's perspective. Yeah, at this zoomed in resolution, you can see that right here, the top voltage is 800 millivolts, which 700 millivolts is what the spec says. So it is even plus minus 5%. It is it's definitely a little high. So finally, what does the monitor look like? Is it correct? Well, here's what I see on my monitor. And as you can see, it's a white rectangle in the middle of the screen, which is what I would expect. Does this mean that it's working? Well, yeah, I think it does, but I think there's some more test patterns that I'd like to throw out on the monitor to see if those test patterns would show up the way I expect. So I've added offline a couple of components to the project. One is a test pattern generator. And what it does is it takes the current row and column index, and it takes whether the signal is active or not, whether we're in the active region or not. And it also takes this pattern ID, which it's a binary number, and we can basically produce and run it through this multiplexer to produce a variety of patterns. And as you can see, the first pattern is whether or not we're in the active area. And if we are, then we're going to, if we're active, we're going to output a 1. So that's going to make this white. This should probably just say output, but anyway. So we'll produce an all whites, screen, basically like we have right now. This one is wired to ground, which means all pixels will be low, which means we should see all black. And then this next one, taking the value of the column index, bit shifting it by 5, taking the last bit that results, and then running it through this AND gate, which is connected up to the active signal, and then outputting it. I'll kind of let you take a guess as to what that might do. Of course, you're going to see it here shortly. And then this last signal is basically an OR gate, which takes the result of either one of these and outputs the signal. So the next component is this component, which again, it's not really important to know what all this does. And in fact, I'm going to be creating a new series called Logisim Bits, which takes some of these little circuits that I've been using and just, 2 or 3 minute video on how they may be useful to you. Again, these things are repeated in electronics discussions all the time, but maybe not in the context of Logisim. But the point of this circuit is I want to hook up a button to my CMOD board where when I press a button, that it basically runs through all of the patterns that are input to the test pattern generator. And so I've got some counters and some logic to debounce as well as increment my pattern so that I can cycle through all of the patterns on the display. So let's wire these two things together to our test harness. So we need a test pattern generator. And we're going to see if we can make all this fit so I don't have to create tunnels for everything. So, again, I have these labels not consistently named, but that's okay. Horizontal in column and vertical in row. And then finally, for our pattern input, that's that multi-bit input that selects which pattern that we want. So that's the purpose of this. And then our debound signal requires the clock. And then, of course, we need a push button. Okay, let's synthesize this. Okay, so we need our button now connected to a button. I'll make it that one. Okay, design is synthesized. Let's load it. And I will flip over to our board. And when I push the button, okay, so the second one was all off, which makes sense. Third one, horizontal, vertical bars. Next one, horizontal bars. Next one, checkers. And then cycle back to the beginning. So I can continue to cycle through these. And that tells me our VGA circuit seems to be working as expected. Thanks for watching.